Today we're going to look at an assembly language programming game called Comet 64. So we go through a fake boot up sequence for our fake computer. The vibe of the documentation is very Commodore 64-like. We're going to make a username here. And here we are with our fabulous 8-bit era computer. The first things first, we get to change some settings. So let's do that. The most important setting, of course, is what color theme you're going to use. So let's see. I actually am very fond of kind of this green screen setting. Let's see what else we've got. MDEC2, Macintosh. It doesn't look like a Macintosh. Oh my goodness. Okay, I think we have to go for this. This would be, of course, what I would actually have been using back in the early 1980s, but this is just so nostalgic. Let's do it. So what have we got here? Well, we have a home screen. On this home screen, we can see we have a few different disks. Takes a little while to read the disks. Oh, we could also turn on sound effects. I think we should definitely do that. Let's see. If I recall correctly, typing sound effects. There we go. That'll make things much, much better. Oh, we have little bleeps and bloops too. Okay, so we can look at these different disks. We can see that each disk has a few puzzles that are unlocked and a bunch of puzzles that are locked. We have a file that seems to be encrypted, so we'll probably figure out what to do with that as the game goes on. We have a place to type our own notes. That's great. We actually have these disks too, with different disks. And what's an A? And every disk, it looks like, has its own user manual too. So let's take a look at the user manual. This tells us a little bit about this crazy computer, and right away we get some instructions about the interface. The goal of the game is to take values from the input, do something to them in our assembly language, and send them to the output. There are actually some other objectives in this game as well, but most puzzles are going to follow that pattern. And in order to do this, we're going to write in assembly language. It's not a real assembly language. It's not like any you've ever used, but it's a pseudo-assembly language. So what we learn is this computer has a number of different registers, which correspond very loosely to types. So the reg register holds floating point values or decimal values. The int register holds integers. Bool holds both bool values and the results of comparisons. String holds string. Char holds a character. The basic syntax is something equals something else. And in addition to something equals something else, we can do some basic math: plus, minus, multiply, divide. We can use as these operands registers, ports, or constants. That's actually quite a luxury. There are some assembly languages that will make that difficult. So here's some examples. To write to a register, just assign it. Register equals 1.4 puts the value 1.4 into a register. We've got some arithmetic. We have a switch operation, which will essentially back up a register, swap it with another register of the same type, basically. And we have some labels, which sadly do take up an entire line in this game. We have jumps. This is the least fun thing about the game, is the jump syntax. So you do a check like this, a check int is greater than 0. That sets a value in the bool register. And then your next line is going to be something like jump if false to this label. All right, there's some more things here. We'll see if we actually need those later. Let's jump in to the very first puzzle. Read the values from input and write them to output after a discount of 20%. So they've given us some sample code here. If you hit tab, it brings up the input and output tape. And we could step through this program and see how it doesn't work. So the first line copied the value 10 from the input tape up here to the int register. The next line is going to divide the int register by 100 and assign it to reg, or reg. Reg equals reg times 20, that's 2. Output equals reg, that 2 should appear down here in the output. So that's not going to work, and in fact, if you just run it, you can see that we've got some tests here. and they've failed. So one thing to note here is that when we reach the last line of our program, we do wrap around to the first line, which is nice. It saves us a jump instruction. You do have to remember to hit tab to bring up your register view. I'm just going to get rid of this because I don't like it. Let's try it from the start. Read the values from input and write them to output after a discount of 20%. So the first thing I'm thinking is, can we do math that targets? Can we do this in one line? I'm positive that the answer is no, but let's explore why not. So let's say, well, why can't we do this? Times 0.80. Will that actually work? Let's try it. Too many operands. Use registers for arithmetic operations. All right, so the problem here is this input, I believe. Let's see, what happens if we do this? Nope. So you actually have to assign the result of an operation, arithmetic operation, to a register. Can we do this? Oh, we need a semicolon. Looks like it's going to let us do it though. So that actually worked. So what that means is input and I guess output is write only, but input can be in an arithmetic operation. It just can't be the target of an arithmetic operation. And right here, this is why most assembly languages don't use this blah equals blah syntax, because it sounds very simple, but it turns out that the various restrictions you have when writing machine code mean that there's a lot of exceptions. All right, so what are we going to do here? We're assigning that value to a register, and then we're going to vector that register into our output, and I think that should do it. Let's try it. Running our tests. Wonderful, and we have passed the test. And even nicer, we can see that we have met the challenge conditions of the fewest number of lines and the fewest number of cycles. I'm going to try to not get too hung up on optimizing for this, because really what I want to show you is the kind of nature of the puzzles you'll be facing. And I'm not going to go through the entire game here. At most, I'll go through this first disc, and if I get bored or I feel like this is dragging on, I might cut it short. Oh, and here we have leaderboards. You could see that I'm the only one of my friends to have bought Comet 64 so far. Well, hopefully that will change soon. All right, why so negative? Input contains negative numbers only. Remove their negativity and output them. So once again, we can go to our user manual and look at our operations. We can see that we do have a multiply operation. So that's pretty deluxe. We don't have to worry about overflow as near as I can tell. In fact, let's test that right now. Can we do this? Let's see what happens. So the answer is yes, we can. This is something that you would not have been able to get away with in a real 8-bit computer. On an Apple II, we would have overflown at the value 256. So input contains negative numbers only. Let's actually solve this for real. It doesn't say whether they are negative integers. Let's assume they're negative integers, and if we're wrong, we'll find out. So we could say int equals input times -1, output equals int. And I've once again forgotten the semicolons. We'll add them. Looks to me correct. We can speed this up. We did it. And once again, this happened to be a perfectly optimal solution. That won't last for long, I'm sure. Read the weight in kilograms, followed by the height values from input, and calculate the BMI. The formula is weight divided by height squared. Okay, well, looking at right off the bat, there's no way to see what's further down the tape, but we can see that our first weight is an integer and our first height is a decimal. So let's assume that that pattern is going to continue. And I'm not going to try and be efficient here this time. Let's say we're going to grab the weight, which is going to be our input. We're going to grab the height, which is going to be also our input. Do we have comments? I didn't notice if there were comments in here. There are, ***. Anything typed after a // I don't know why I said ***. Okay, so let's comment our code. The formula is weight divided by height squared. Well, we know we can't do things like we can't do this. It doesn't support kind of more complicated or nested arithmetic. So what we can do is we can square the height. And then we can divide by the weight. Or divide by that height squared, rather, excuse me. And once again, no, I do have my semicolons there. All right, let's see what happens. Okay, 111 is in our int register. 1.63 is in our reg register. We've squared it. We're going to divide int by reg. We get that. We're going to output that. Does look like a BMI. We can run it. We can run it fast. And we've passed all the tests. Wonderful. Looking pretty good so far. Ignore the input for now and output all the numbers from 1 inclusive to 100 inclusive. Well, there's the right way to do this, and then there's the cheesy way. So let's do it the right way first. And this might be one where I am going to optimize, but we'll start off doing it the right way. So we know that we want to start at 1. Well, if we're guaranteed that int is 0, then we can make some assumptions. But I'm going to not make that assumption. Let's go ahead and do this the slow way. We're going to initialize int to 0. We're going to add a label. We're going to increment int. Lovingly, we can use constants to do that. Then we're going to output it. And then we're going to jump to label. Okay. So I believe that this will work, and this will not be as efficient as possible. I'm also making the assumption here that when we reach 100, it's going to stop. That may not be a good assumption. Maybe this will loop forever, and let's find out. We needed a conditional to stop at 100. I'm going to speed through this, obviously. Great. And it actually let us get away with it. On a real computer, a real program, this would be terrible because we would never stop until the user interrupted or the machine crashed or the universe died of heat death. We can see that we failed both the line challenge and the cycle challenge pretty badly. So doing the line challenge is actually very easy because I think all we have to do here is remove our assumption. And if we remove our assumption and rely on the fact that we know int is initialized to 0, then we don't even need a jump or a label because we know that when it reaches the last line of the program, it will wrap around to the beginning for us. There we go. And this is going to meet the two solutions. Could we do better? Well, unfortunately, we could. I referred to the cheesy solution before. We know that there are 100 values to be output here. And we know that the system supports constants. And we know that there is no limit on the number of lines you can add. So if you really wanted to, you could just start doing this. It would be pretty boring video for me to show you me typing all of these things, wouldn't it? Well, I'm not going to do that. I'm going to cut it here. And we're back. You can see we have written our program, and it turns out I was actually mistaken about something. There is a limit on the number of lines. It's 100. Normally, if we wanted to simply write these output values, 100 of them, we would not be able to do that. However, what I did here is cheated, and in the last few lines wrote essentially our small 5-line program, but only starting from the number 94. Let's see if it worked. Oh, I forgot an equal sign. Okay, it worked as expected. That's great. And now we can see we've beaten the cycle challenge, and we can see that we've failed the line optimization challenge by the most possible. So that is at least interesting that we see that the trade-offs between time and space are present even in a toy computer like this. So this looks like the inverse of what we just solved. Output a countdown from 100 inclusive to 0. Ignore the input. Okay, I don't see why we can't do almost the same thing, right? 100 inclusive. And then decrement. And then jump. Again, same sort of caveat as before, where we're not actually checking the boundary conditions here. We're trusting that it'll stop us when we get there, because it's a puzzle game and not an actual computer. All right, compare the pair. For each 2 values from input, output the greater one. Okay, so here we are probably going to have to do some actual comparisons. So this will be the first puzzle where we're going to use the check directive that's discussed in the user manual. So each 2 values, we're not given any explicit guarantees about type, but it looks like they're integers. The reg register can hold an integer. It's not going to promote it into a decimal just because we're using it, so we may end up using both of those here. Well, let's be naive. We can just say put the first one into our int, put the second one into our reg. I'm going to flip back and forth between saying reg and reg. I don't particularly have a bias on how to pronounce that. So now we have 2 values in our registers. We could check one. Okay, well, how about check if, no, that's not right. If the integer register is bigger, then we can, the way they do the jump commands, let's say that if the integer register is bigger, we're going to continue with the flow of control. And if it's not, we're going to jump. So we're going to say jump if false to a label we haven't made yet. We're going to make a new label here. So now we're in the true branch. So we're going to say output is int because int was bigger. And then we're going to jump to the loop. And now we're in our out branch. We're going to say output equals reg. And we don't need a loop here because it will loop back to the beginning. I'm very confident this is not the most efficient program, and I don't care. Okay, how bad were we? Yeah, we're pretty close. I'm just going to go on. I don't think it's interesting to watch me thinking about how to interleave these jumps to be efficient. Input contains a list of dates, but some dates are written twice in a row. Output only the duplicates. Gosh, that's rather interesting. These dates look like they're ints, so we can start there. So now we have a date in a register. We're going to, oh, and I should have said this back at the beginning. Dereferencing the input or the output stream immediately moves it on to the next value, and there's no going back. You can't move the tape backwards. If once you read from the input, you've advanced it. Once you write to the output, you've advanced it. So we're relying on that to do our indexing through the input here. And that makes it this challenging because if we read to check whether the next input is the same as the one we just did, that value's, and it wasn't, then it's gone. right? So we have to read this next value into memory no matter what, even if it's the same. So there are effectively two cases here. The first case is that reg and int are the same, in which case we'll do a jump if true here. In which case we're going to output int, throw away reg, and read the next value. So we would be outputting int, and then we're throwing away reg. We can throw away reg and read the next value at the same time by doing that, right? So that's one case. That's the case when they are the same. If they're not the same, we are outputting nothing, throwing away int, which we'll do by promoting reg, and reading the next value, which is going to be, again, like that. Is that correct? I think that's correct. So really, if we always did this, because in the same case it would be safe to do this line 6. So we could probably optimize our jumps a little bit. If we really wanted to. Well, I think the logic here is sound. So again, I always get kind of caught up trying to optimize this stuff. Let's see where, I'm sure this isn't correct. I made some sort of mistake. Let's see how it goes. I'm going to step through because this is pretty confusing to me, having to think in two time streams at once. Okay, we've got both our values in memory. Oh, I already see where the bug is here. Okay, we're going to, are they the same? Yes. Output 1. Second opera, I did it again. I always want to say output int, but it's output equals. Okay. Register equals input. It's different this time. Are they the same? No, they're not. Bool goes to false. This conditional will fail. Therefore, copy that. Oh, you know, maybe this will work. Well, let's run it. Okay, wow, that actually worked. I was sure that I would have made some mistake there. So we actually did it in the fewest number of steps, but we could have optimized how we did our jumps here, and that's a pretty common failure mode. In games of this type, TIS-100 or Shenzhen I that judge you on this space and time criterias, it is pretty common that often you'll need more than one solution to be fully optimized. So you'll write one solution that's optimized on number of lines and one solution that's optimized on number of cycles. And we are not doing that today. Because 0 marks the end of a package. Output the sum of every package. All right. So can we have a 0 length package? Let's assume we can. So we're going to check on input, and we'll use int as our accumulator here. We're going to assume that all our registers are initialized to 0. So we're going to take that. We're going to check if it's greater than, we'll check if it's equal to 0. Output's a keyword. We'll jump to out, in which case we will that. Again, I'm not going for efficiency here. Right? If it's false, then we're going to add it to our int register. And that's all. Could I do better? Well, if we did what if we made this jump if false? Yes, we can do better. So let's make this jump if false, and we'll call it continue. And this is going to go down to continue. This is going to come up here. Uses your normal cut, copy, paste editor keys for this sort of thing. And now, if the register is 0, we're going to immediately output the contents of int. We're going to reinitialize int to 0. We don't need a jump here because we're going to add int to do that and initialize both registers. This continues to be 0. We don't need this jump either because we're going to jump right back to the beginning, and we don't need this label either. All right, let's see how many mistakes I made. We passed. That's good. Look at that. We beat the challenge. That's pretty great. I feel really clever about this one. Only 2 more. And you'll see that as we've started revealing these things, suddenly this code has appeared. And I don't know what that means, but I bet it's got something to do with this protected file. All right, let's go back on to the next puzzle, roundabout. Input contains decimal numbers only. That's nice that they've told us that. Round them to the nearest integer before outputting. The nearest integer. So this is not a truncate. If it were a truncate, we could just assign these values to the int register and we would be done. So first, since they are decimal values, floating point values, whatever you want to call them, we do have to read them into our register. Now they're into our register. What are we going to do? Well, so they don't quite say, but I assume we're using the standard definition of round here, which means that if something is exactly, say, 4.5, we round it up to 5. And if it's 4.4999, we're going to round it down to 4. All right, so if we do this, it will truncate. And we can then, right, we don't need the original value handing around. So now we can say that should leave us just the fractional part. At which point could do a straight comparison here, I think. So we can say check if reg is less than 0.5, right? Because if it's equal to or greater than 0.5, we want to round up. If it is less than 0.5, let's do the true case first. If it's less than 0.5, we just output reg and we're done. No, sorry. Output the truncated number. I'm going to go ahead and not try to be efficient here. If it is greater than 0.5, then we're going to output that. I'm assuming it'll let me do that math. It might not. It might require me to. And this is the same thing where it doesn't want me to All right, let's see if we did it. Second output. I'm bad at assembly language, folks. All right, did we do it? That was correct. Again, it feels a little ugly. I'm sure this is not optimal, and indeed it's not even close. That's fine. Let's go on to input contains integer numbers only. Round them to the nearest 10. So we could actually potentially use our old code to do this, right? Let's see. Okay. If we want to round them to the nearest 10, so we're going to have numbers like 34, 35, 36, right? So really what we want is we want that last number. Well, again, I think we can use the same logic. So if we know these numbers are integers, let's read it into the int register. Then we know that if we divide it by 10, we would end up with that. Right? So let's do that. Being very careful to put a semicolon on every line here. I'm just putting that comment there to annoy people who hate obvious comments. Okay. Then we're going to do the exact same thing we did before. We don't need our original input at all here. Now we've truncated it. Now we have the decimal part only, and I forgot a semicolon. And then we check if, let's do the same logic as before. I don't care that it wasn't efficient. If reg is less than 5, here, we'll do it the other way this time. We're going to we'll jump if it's true. Right? Is that what I did last time? Yeah, last time I did jump if false. Let's do jump if true. If it's true, then we're going to round down by 10. So now we're in the false case where we're going to round up by 10, which means our int goes up by 1 and then is multiplied by 10 and then is output. And again, I'm going to just be super inefficient here and add an extra jump. Now we are in our round down case, in which case all we need to do is that. And you can see we've duplicated some code here. So if we were going to try to refactor this, getting this duplicated code to be written only once and threading our jumps accordingly would be how we did it. So let's see. Looking carefully to make sure I've got all my semicolons. There's a semicolon there. I wonder if somehow the comment is throwing it off. I'm going to remove these comments. You know, I think I had an extra space here, and I think that might have been what was throwing it off. Okay. Yeah, it's looking pretty good. Oh, what do we get here? Second operand after jump. Ah. Okay. All right, and how badly did we do? Pretty badly. We could work on optimizing this a lot more. So this is about, I would say, a little less than 1/4 of the game. And I obviously don't want to play through the entire game. I really do encourage you, if you like the idea of, you're not actually learning real assembly language, but if you like the Zectronics games, if you like games like Manufactoria, this is kind of it's going to engage those same circuits in your brain. This kind of renaissance we're having in the past few years with faux retro games. I just think it's fantastic, and I really hope we continue to put out games like this. Right now, Comet 64 is available on Steam. It's $14.99. It runs on Windows and Mac OS, and I believe also on Linux as well if you have Steam on Linux. Check it out if you want to. This has been Gaming Like It's 1979. Thanks for watching.